In this unit, we're going to pick up and look at projectiles. In year 12, we did look at projectiles, but only when they were moving in one direction, as in a ball that's thrown vertically upwards. And we made use of some Suvat equations, and we had to think about the direction that we chose as the positive direction and acceleration. We're going to do a similar thing, but this time our projectiles are going to be moving in two directions. There will be some vertical movement and there'll be some horizontal movement. To ensure that we have a good understanding of the situation we're working with, the context we're working in, we want to make sure we can model it well. And the modeling starts with a good, well-structured, fully labeled diagram. The diagram helps to keep us oriented in the problem, so we know all the pieces of information that might be useful and what might be potential next steps in coming up with a solution. Secondly, we once again have the opportunity to work with the vertical and horizontal components independently or individually, even simultaneously. Sometimes they will cross over and there's some sensible assumptions we can make that will help to move from one to the other. Okay, we're going to start by thinking of objects that have been projected horizontally. So actually there is no initial vertical movement. We've shot it out exactly horizontal, parallel to the ground, parallel to the x-axis. Well, let's take a look at the model that I've started to produce. It comes from this question, where we've been told that the particle is projected horizontally. The speed it's projected at, or the velocity it's projected at, is 25 meters per second. And that's from a point 78.4 meters above the horizontal surface. All right, so I just started by modeling the ground and just a wall or a vertical point for which I can measure or identify the 78.4 meters. I've drawn the initial line of projection and I've labeled that as 25 meters per second. I've also drawn a flight path for this projectile, showing and demonstrating that it is going to fall to the ground over time. Okay, we can make a start on trying to respond to the question. Find the time the particle takes to reach the surface. Well, the object moving towards the ground is vertical motion. So we'll just look at the vertical components of the motion that we have here. So we'll label it as vertical and we'll set out our Suvat variables as usual. I'm going to choose down as the positive direction. This is because the object never moved up. Its initial vertical motion was down. The initial vertical velocity is 0 because we've launched this horizontally. There was no vertical component to the initial projection. All right, so the displacement 78.4, initial velocity of 0. I don't know the final velocity. I know the acceleration is g, 9.8, and I don't know the time it takes, but I'm looking for the time. So we just choose an appropriate Suvat equation, and we can do s equals ut plus half at squared, and go ahead and substitute our values in. Rearranging, we should easily be able to find the value of t. At this point here where we square root, you want to be really careful. Only one of the square roots will make sense. T equals 4. You will actually be penalized if you do state t equals -4, because that wouldn't make sense in the context. We can't say that the particle hits the ground 4 seconds before it was even thrown. So just be really careful there that you don't just blindly solve and do the maths, but you're thinking about the context and what these values actually mean for the problem and scenario we're working on. Okay, so let's move on to part B. We want to find the horizontal distance traveled in the same time. All right, so we're just going to look at horizontal components now. There's something we need to be really careful on. Let's set up these Suvat variables and we'll fill in what we know. Horizontal displacement we're looking for, we don't know what that is. The initial horizontal velocity, 25 meters per second. The final horizontal velocity, Now, this is the important part. The acceleration, the change of velocity in the horizontal direction, or for the horizontal component, is actually 0. There is no acceleration horizontally. Let's think about this. Vertically, there's acceleration due to gravity. Gravity is pulling the particle, it's pulling the object down towards the ground. There's no comparable accelerating force that is moving something horizontally. So whenever you're working with the horizontal component, there is no acceleration. The initial and the final horizontal velocity will always be the same. All right, with that in mind, let's carry on. So the initial velocity, 25, final velocity, 25, acceleration, we can just put in a 0. The time, well, the time is the same time it took to hit the ground. So we're going to put that in as 4. All right, choosing a sensible Suvat equation. S equals ut plus half at squared seems to work again. Well, we know the acceleration is 0, so the whole of this second part is going to be 0. So we can just think of this as S equals ut. If we're looking at a horizontal component, S equals ut. And that's simply going to be 100. All right, so the horizontal displacement is going to be 100 meters. So this is how I want you to approach these questions. We're going to get a good diagram. We're going to think about the vertical components, and we're going to think about the horizontal components. For the vertical, we're going to use the acceleration due to gravity, and for the horizontal, there will be no acceleration. The nice thing about using components, or an interesting thing about using components, is that if a ball was actually dropped straight down, at the same time this ball was projected horizontally at a velocity of 25 meters per second, they would both actually hit the ground at the same time. Both of them would hit the ground at the same time. So that's part of the reason why we can just think about the vertical components and the horizontal components separately. And then the time that we used for the vertical component is also the time that we use in the horizontal component. So there's that independent, simultaneous crossing over of those two components, horizontal and vertical. Okay, so just moving forward into the next question, where we're not specifically looking at where the particle hits the ground, but we're going to look at some other point on the flight path. So here we're told that the particle is projected horizontally with a velocity of 15 meters per second, and we want to find the horizontal and vertical components of the displacement of the particle from the point of projection after 3 seconds. So 3 seconds after it's been projected, where is it? We want the horizontal and the vertical component. All right, so I'm just going to go ahead and draw the flight path, and I'm assuming it hasn't hit the ground at this point, so I'm just going to indicate the point I'm interested in. T equals 3. That's the only thing I know about that point at this moment, that the time that this particle has been in flight is 3 seconds. Okay, so same strategy as always. We'll go for our vertical components and horizontal components separately. All right, so vertically, let's set out our Suvat variables. Which of them do we know? Which of them do we need to find? So we're interested in the displacement. We don't have any idea what the displacement is. We know the initial vertical velocity is 0. The final vertical velocity, we don't actually know yet. And acceleration, since down is our positive direction, the acceleration is going to be g, 9.8. The time is 3 seconds. We do know that. All right, just a reminder, we're looking for the displacement there. So out of our Suvat equations, we're once again going to use S equals ut plus half at squared. And we'll go ahead and just substitute our values in. So we're looking for S, we'll use u and t. U being 0 makes the whole of that term 0. So we've really got half at squared. Half of the acceleration is 4.9 times 3 squared. Straight into the calculator, we get a displacement of 44.1 meters. All right, it's 44.1 meters below its original starting point. So we can add that to the diagram also. Okay, next we'll just look at what is happening horizontally. Okay, so the horizontal projection, or the horizontal components. Let's just get all of our Suvat variables again. All right, once again, the acceleration is going to be 0. There is no acceleration in the horizontal direction. We're looking for the displacement. The initial velocity is the 15. Final velocity is also 15. And we know that the time is going to be 3 seconds. All right, similarly, we can go ahead and use S equals UT. We don't have to use the whole equation as we saw last time. S equals UT will be fine. Okay, 15 times 3 gives us 45. So here I have the vertical and the horizontal components. The vertical components for the displacement are 45 meters and 44.1 meters. Okay, in part B of the question, we're asked to find the distance of the particle from the point of projection after 3 seconds. So here, we just want the direct distance. And hopefully you can see from the diagram, we're looking for the hypotenuse of a right-angled triangle. So I'm going to remodel this with the horizontal and the vertical components, which are found in part A. I can label them on this triangle, and we're looking for the hypotenuse. So straight away, we should know we're going to use the spot of Pythagoras. D squared equals the 44.1 and the 45 squared and added together. Into your calculator, couple of steps, we should be able to get that the distance is 63 meters to the nearest whole number. In this final example, we see that we're working with unknown initial velocity. We still solve this in the same way we've solved all of our problems up to now. We get ourselves a good diagram and we consider the horizontal and vertical components separately. So, the initial velocity, the flight path, and the displacement, both horizontal and vertical, that we were given in the question. Let's get to the components. So, the vertical, for our Suvat variables, we know the displacement. We know the initial velocity is 0, since this was projected horizontally. We don't know the final velocity, but our acceleration is 9.8, as usual. Now, the time here is unknown, but we're going to try and find the value for this time. All right, so choosing the right Suvat equation, S equals UT plus half AT squared, substituting in all the variables that we have, and then we're just going to rearrange to find T. So from here I can see that T squared should equal 122.5 over 4.9, or actually T is the square root of that fraction. And from there we get that T equals 5. So it takes 5 seconds for the particle to hit the ground. Okay, let's move on to the horizontal components. Now that we know the time it takes to hit the ground, we should be able to find this initial horizontal velocity. See that variables, we'll fill in everything we know. Displacement of 90, initial velocity and final velocity are both unknown u. 0 for the acceleration and time of 5 seconds. And so we'll make use of our usual S equals UT, which we use for horizontal projection. Substituting in our values, we find that the initial velocity must be 18 meters per second. Okay, so we've seen a variety of different unknowns: unknown velocity, unknown distance, unknown components, unknown displacement, etc. All of these can be found using the same strategy and the same technique and the same approach. Draw a sensible diagram, label it well, split your horizontal and vertical components up, and using your variables, decide which suit that equation will be useful. This will always yield some more information that you can use to step forward in your problem solving.